Hello, everybody. So what we're going to be doing today is we're going to be doing section 2.6, which is on quadric surfaces and cylinders. So cylinders is not the main topic of the day, but it is the quicker topic. So we're going to do cylinders first. So in section 2.6 in your book, it starts out with a section that it says identifying cylinders, right? So uh, yep, it's a cylinder, right? You looked at it, you see it's a cylinder. Yep, it's a cylinder. Okay, now we're on to quadric surfaces, right? Not quite. That's not, it's a little bit more complicated than that, than just going, yeah, we know that a cylinder looks like a tin can type shape. So for us, a cylinder is slightly more complicated. So what you're going to do is a cylinder for us is going to be you have a curve written in terms of two variables. You have a curve in terms of two variables. So a very quick example of that would be something like this. X squared plus y squared equals 9, right? That's a circle. Okay. But, um, so that's number one thing you have. Let me actually move this so it looks a little better. Okay. So you have a curve in terms of two variables, like, for example, this one. And then we're in 3D space, though. So if they don't list one of the variables, like this has X and Y, but the third variable is missing, there's no Z. So we're in or we're in 3D. So there should be three variables. So the one that they don't list, which is Z in the example I just showed you, we didn't list. The one we did not list in the equation, I shouldn't say it that way. The one that didn't appear in the equation, that one can be anything. Okay. And if you have those two things happening together, then that makes a cylinder. This is what a cylinder is. Okay. For us, in this class, this is what a cylinder is in Calc 3. So let's just think about that example that I just did, right? So we have this equation. So I say plot the surface x squared plus y squared equals 9. Okay, so the idea here is in the xy plane, so here's an xy plane, we know that this is just a circle. So you can just plot a circle, say, well, there it is. That's what we're looking at, right? So this must be at 3, -3, +3, -3. So you have that, right? But if you look at the plot in 3 dimensions, where you got, that should be x. Don't know why I wrote y. X, straight line, come on. Y, z. Then if you plot this circle in the xy plane, then it just looks like trying to plot this evenly here. Don't know if I can do it. That's really helpful, computer. Thank you. No. Why won't it do it? I know it can. Okay. Why? Super annoying. I don't know why it will not make a cylinder. Oh, there you go. Okay. This is going to have to be good enough. So sorry. Make it a little bigger this way, make it a little bigger this way. Okay. So there you go. So you have a circle on the ground on the XY plane, but the Z value is not listed at all in this equation, right? There's no Z there. So since there's no Z there, all Z values are possible. So that means you can take this entire circle, which duplicate, you can take this entire circle. Why? Today is not a good day for this. It just won't let me move the things after I put them down because my life is terrible. That's why. Copy. Okay, I just paste it. Paste. And it still won't let me. Fantastic. What is wrong with the world? All right. So it could be any Z value. So it could be that Z value that I just posted. Or it could be this Z value, right? An even higher one. So you can just plot that same exact circle at any Z value you want because no Z value was given in the original equation. So because of that, like all of the circles that I just posted are actually part of the surface. And in fact, just kind of connect the dots here on the edge, all of that is the cylinder. Okay, so hopefully that made some kind of sense. Plot the surface. So in the XY plane, it's a curve, but then you allow all possible Z values, and then you get this. So I think you could, maybe it would be better if you saw it this way. So technically, when we write x squared plus y squared equals 9, what we mean is this. What we mean is the set of all x, y, z values that satisfy that equation. And that's why the z value is allowed to be anything. So z may be any value. But the x and y have to lie on that circle. So does that make sense? So you've got like on the x and the y are always going to be on a circle, but the z value can be any z value. So it's that circle extended up and down forever. Okay? And any kind of shape that works that way is what we call a cylinder in a Calculus 3 class. So for example, it doesn't have to be like an actual cylinder, right? If I do this, like if I say, you know, plot the surface, or I'll say cylinder because it's a cylinder. Let's say, let me think. Thinking is hard. X and Y. I don't want to do X and Y. Which variable is what? I'm going to do X and Z. Plot the cylinder, Z equals X squared. Okay, so there's a C there. Okay, so we want to plot that cylinder. So again, you want to think of it as what I just wrote, right? It's technically the set of all x, y, z such that z equals x squared, right? So the y value is allowed to be anything. So if you think about the 2D plot, the 2D plot of the curve z equals x squared would be, well, it's like a two-dimensional plane. So you put x there and z here this time. Then what kind of curve is z equals x squared? Well, it's the same as like y equals x squared normally is, right? This is a parabola. So we know that this is a parabola. So you can just plot it. There we go. So it looks like a parabola, goes through 1, 1, negative 1, 1, 2, 4, which, I'm not going to plot this like really good or anything, but negative 2, 4, etc. So that's what the curve looks like. But then when you look at it on a 3D plot of the surface, then you've got your y here, x here, z here, right? So where's the xz plane, right? Because this was x and z. So where's the xz plane? Well, x is here, z is here, right? So if you extend this back this way, maybe we can do a little better than that. Make it a little straighter. Then this is all like this right here. That's the xz plane. So if you plot the parabola in there, then you get a parabola in there, right? So it goes through 0, 0. So then it's going to come up. And it's going to come up this way, right? So you get that parabola. But that parabola can be anywhere on the y-axis, right? Because the y value is not being restricted by this equation. So you can take this parabola and move it forward or backwards along the y-axis. So it can go that way or that way along the y. So you can take this, duplicate it, did not. Because it must be in 2 pieces whenever you draw that parabola to avoid this issue. Okay, good. Good enough. Okay. So you can slide that anywhere along the y-axis. So you can slide it that way. And also you can, how did that happen? You can slide it this way, like that. And then to make a surface out of it, you would just say, well, okay, well, like the top next there, the top on the other side is there. So it's like this. Kind of scoop shape, right? So like this middle here, like the middle here is all empty. So it's like skateboard half pipe. That's what I just drew, right? And technically this extends up forever because the parabola does extend forever. Okay, and so that's technically a cylinder there, even though of course this doesn't look like a regular cylinder, what we know as a cylinder. All right, so anything that satisfies this property is going to work this way. So you're just looking for what we said here, a curve in terms of 2 variables like this. That means the third variable has no restrictions on it. So you always have this issue where, not issue, but you always have this situation where there's a 2-dimensional curve that you can draw, and then you can move that along the axis of the other variable that's not listed. So there's no z, so you can take your circle and move it up and down on the z-axis. Here we have z and x, so we have a parabola in z and x, but you can slide it left and right along the y-axis because there's no y given. And that is a cylinder. Okay, so that's the main thing. So there's definitely some examples of those. You can plot them. I think you can plot them in GeoGebra or Wolfram Alpha. If you want to interact with them, you use GeoGebra. If you don't care, you use Wolfram Alpha. So like if I come over here, like let's say I wanted to plot this cylinder, right? Um, what would I have to type in? Well, I'd have to type in the equation of the cylinder. So the cylinder was z equals, I have no idea what just happened to the cursor there. Z equals x squared. And there you go, right? Just what I drew. So that is a cylinder, and that is a cylinder, technically. Right? Now, if you change the variable here, like if you change it to, instead of z and x, you change it to z and y, that just now oriented it along the other axis. So you, as soon as I hit enter there, like basically the shape just turned itself 90 degrees. Because what was happening was, instead of having this same shape along the y-axis, it was along the x-axis if you change the x to a y. Okay, so those are cylinders, and there's not a lot to say about them other than what we just did. If you're trying to graph them, I would recommend that you do what I just did. Graph them on GeoGebra, and it's an easy way to see them. Now, I said you could use Wolfram Alpha as well. You certainly can. If I go Wolfram Alpha, z equals x squared. It says it's a parabola, but how would I make it do it? I don't know. Maybe if I tell it a cylinder or a surface. Oh, okay. Maybe Wolfram Alpha is not the way to go. Surface, because it doesn't know that we want. It doesn't know that it wants me to add. No, that's a surface of revolution. Okay, don't use Wolfram Alpha unless you can figure out how to make it understand that there is a y variable that we didn't type in. Okay, so maybe stick to GeoGebra for now for this. All right, enough of that. I mean, we're going to be coming back to GeoGebra a lot. So those are cylinders. Now let us talk about quadric surfaces. Which is the main. Okay, quadric surfaces. So they're very simple. That's a joke. Quadric, not quadratics, quadric. Quadric surfaces are the graphs of equations that can be written ax squared plus by squared plus cz squared, right? So all the variables can be squared, second degree equation. But because we've got multiple variables here, there's other ways to get a second degree like a second degree type thing. You can have a constant times an x and a y. That's second degree, right? If x is a variable and y is a variable, there's two variables multiplied, so that still counts as second degree. You could have a constant times x and z. Same thing. It's also second degree. You could also have y and z. That's also second degree. So these are hopefully all of the second degree variables that you might have. But then you could also have first degree, right? First degree equations are included in second degree. So constant times x, constant times y, constant times z, and then you can have an actual constant, and all of that equals 0. Okay, so that looks like nonsense, right? But what this is just a generic second degree equation for x, y, and z, right? Just like if I did ax squared plus, if it was only two variables, you'd go ax squared plus by squared plus cxy. Like that would be all of the second degree possibilities. And then you'd have the first degree possibilities, and then you would have a constant, right? So like every possible way to get a second degree term, then every possible way to get first degree term, and then every possible way to get a 0 degree term, which is a constant. Set all of that equal to 0, and that's just a generic equation. Okay, now what do you do with this? Nothing. You do nothing with it. Okay, that's just what a generic second degree equation looks like. We're going to look at specific second degree equations. Okay, so specific ones. So our first one we're going to do is we are going to plot an ellipsoid. And we're going to also like list out the possible shapes that you're supposed to know, how you're supposed to graph them, and so on. Now, you always have access to a computer to help out, which is nice, but you can do all of this by hand. So let's sketch an ellipsoid. Example. Sketch an ellipsoid. What's an ellipsoid? X squared over 2 squared, they say, plus y squared over 3 squared, plus z squared over 5 squared equals 1. So if you had one of those variables gone, right? So just like x squared over 4 plus y squared over 9 equals 1 would be an ellipse in 2 dimensions. So just like that would be an ellipse in 2D, if you add the third variable, all three are squared. Add the third variable, z squared, to get an ellipsoid. Great, what's an ellipsoid? Okay, and so what it is it's going to be, it looks like an ellipse. It's an egg. It looks like an egg. Okay, that's what it looks like. And in terms of the numbers, right? Normally when you were doing an ellipse, right? If you did like x squared over 2 squared, that would mean that the ellipse was plus and minus 2 in the x direction. Well, that's still what it means. So like if you come over here, you go like, this is x. So plus 2, minus 2 on the x-axis. And then for y, we have y squared over 3 squared. That would be plus or minus 3 on the y-axis. So you go 1, 2, 3. So there, there, there. And then this way, -3. So you have like an ellipse there. Now for the y-axis, sorry, z-axis, you've got z squared over 5 squared. That would be plus or minus 5 on the z-axis. So up here at plus 5 and down here at minus 5, it'd go up to there and it would go down to there. And so there's an ellipse in that direction as well. But anyway, the overall shape is basically go around the edges here. I'm drawing this terribly. like an egg shape. Okay. So you can read these numbers here, and they would tell you plus or minus 2 on the x-axis, plus or minus 3 on the y-axis, and plus or minus 5 on the z-axis. And that would get you that shape. If you don't believe me, right, we can come over here to GeoGebra and we should be able to plot it. So let's just delete what we have, delete, delete, and we are going x squared over, it was 4, plus y squared, it was over 9, a plus z squared, and that was over 25, and that was all supposed to equal 1. Enter. And because I accidentally got rid of the cursor one time, oh, why did you do this to me? That's really frustrating when it does that. This is not the best thing to navigate with like an iPad, unfortunately. So I'm typing it in again. If you press the wrong key, then it will like add that like a of xy equals thing that I did not want it to do. Okay, there we go. Enter. So there's our egg shape. And if you look at the numbers, or if you can tell, then you should be able to see that the numbers are what I said they are, right? Like if you look at the green, you can see that the edge of the, if you look at the G, you can probably see that the edge is at 3. So that must be the y-axis. You turn it sideways, you can see that it's plus or minus 2. That must be the x-axis. And if you look at the z-axis, which I guess it doesn't go up to 5, but if you, okay, that now it goes up to 5. So on the z-axis, it's up to plus 5 and down to minus 5. Okay, so there you go. All right, so how would you identify the ellipsoid? So you would identify it based on the signs on the x, the y, and the z. So we would recognize like x squared over a squared plus y squared over b squared plus z squared over c squared equals 1 as an ellipse. Ellipsoid. Ellipsoid. As an ellipsoid. Okay? And so specifically notice that all 3 variables are second degree. They're all on the same side of the equation and they're all positive. That's what you need to notice, right? All 3 of x, y, z are on one side of the equation, are second degree, on one side of the equation, and positive. Okay, that will be what you need to look for, right? If you change what I just said there and make it not true, then it's a different kind of shape. So like if I go up here and I add a minus sign on here, it's not an ellipsoid anymore. If I add a minus sign here, it's not an ellipsoid anymore, right? If I make one of these first power instead of second power, it's not an ellipsoid anymore. Okay? So that's what you have to look at to recognize which shape is which. There will be a summary when we're done, but for now, that's an ellipsoid. Okay? Now, those aren't hard. Ellipsoids, the way that we just did this one, are pretty easy to plot, but not every shape is easy to plot. So we are going to talk about how you would do that. So here is a shape. And I'm going to say example. I'm going to say, plot several traces, which we haven't defined, traces, and then graph the elliptic paraboloid, x squared plus y squared over 4. Or I'll say 2 squared. No, I won't. I lied. Yeah, I will. I'll say it the way they did. Equals z over 5. Okay, so that's what we're trying to plot. So the first thing we need to deal with is what's a trace? And then after we do that, then we can figure out what an elliptic paraboloid is. Okay, so what are traces? So what traces are is if you fix a variable, there's 3 variables here. If you just set one of the variables to be equal to a constant, then you would get only 2 variables left, right? Like, so if I say z equals 5, then this is just 5 over 5, which is 1, and you only have the other 2 variables, x and y. So that would give you a graph of just x and y, which is a 2-dimensional plot of, in this case, an ellipse. Now, if you took a different variable and set it equal to something like, let's say I set x equal to 5. Well, now this would be 25 here, and you just have y and z. And you'd have to say, well, what graph do you get? Well, I don't know. Okay, so that's what traces are, is when you set a variable equal to something, then you can plot the 2-dimensional plot of the other 2 variables. Let me write that so we can see it. So traces. So you set one variable equal to a constant. And make a 2D plot of the curve that you get from the other 2 variables. Now, why would you do that? Because it will help you make the 3D graph later on. Okay, so that's why we're doing it, because we think it will help us later on. Okay, so we got this equation here, x squared plus y squared over 4 equals z over 5. So, so let's do some traces for z. So let's do some traces. So if we set z equals 0, what do we get? Well, if we set z equal to 0 in this equation, z over 5 is going to be 0. So we're going to have x squared plus y squared over 4 equals 0. Now, what does that graph look like? I mean, you probably have not seen this kind of equation very much, but think about it. X squared is always positive or 0, right? X squared has to be greater than or equal to 0 because it's squared, so no negatives. Same thing here. Y squared has to be positive or 0. So if you take something that's positive or 0 plus something that's positive or 0, the result is either positive or 0. In this case, it's supposed to be 0. So in order for this to be 0, actually x and y both have to be 0, right? There's no other value you could put in for x and for y that would satisfy this equation. So you would need to realize that this equation, the only thing that satisfies it is x and y are 0 is the only solution. Okay, now let's set z equal to something else. Now you can set it equal to whatever you want. I'm going to set it equal to 5 just because I know I'm going to divide it by 5 and that just makes it easier to write. So I'm going to say z, what happens as z equals 5? Then we get x squared over, no, nothing, just x squared, plus y squared over 4 equals 5 over 5, right? Which is 1. So I'll just put 1. And what does this look like? Right? Because we're supposed to be graphing this now. So you would need to look at this, realize that it's an ellipse. And specifically, it's an ellipse that goes plus or minus 1 on the x-axis, right? Because this is over 1. And then on the y-axis, with this being y squared over 4, that would go plus or minus 2. So 2, negative 2. And this is x, this is y. So you get this kind of curve. Okay. Now, already, actually, we actually have enough information to plot this, believe it or not. At least if you've already plotted a few of these, you can probably figure it out. So our 3D plot, which I'll put down here, but I'll probably just move it soon. Get out of the way here. X, Y, Z. So here's the idea. This first trace was at z equals 0. Where is z equals 0? Z equals 0 is the plane, right? Z equals 0 is the ground, right? Like here, right? That's z equals 0. Now, where is z equals 5, by the way? Right? Because our other trace was at z equals 5. Well, that would just be up here at z equals 5, right? So up here, this would be your z equals 5 plane. And what we discovered was that our three-dimensional picture at z equals 0, we just have 0, 0 is the solution. So that's just a single dot at 0, 0. Okay. Now, at z equals 5, we have this kind of shape, which is plus or minus 2 on the y-axis, plus or minus 1 on the x-axis. So, this actually intersects somewhere like there. But so on the x-axis and the y-axis here, you've got plus 2 there, minus 2 there, plus 1, minus 1. You have a shape like that. Okay. And we didn't plot them, but like if you made like the z equals like 2, what you would get is x squared plus y squared over 4 equals, and it was, what was it, z over 5, right? So that'd be like 2/5. And if you plotted that, what it would turn out to be is just a, oh, that was not what I wanted. It would just turn out to be a smaller ellipse. Because you'd have to multiply this by 5 over 2, and this by 5 over 2, and this by 5 over 2. You just get a, wait, would you? Yeah, I guess you must. Yeah. So you would just get, something like this. Now we didn't actually plot that, so I'm cheating here, but like we would just get like a smaller thing like that. And And so once you have several of these traces, what you do is you say, oh, okay, I see. The outside of the surface is this circle, and then a smaller circle, and this single point. So actually, the surface looks something like this. Okay. Now, I didn't really do enough traces. I only really did two, right? And then I made one up. But we can do other traces as well. Like, why are we setting z equal to something when we could also set x or y equal to something? So if you do traces like that, what would we get? So let's see here. So for other traces, what could we do? Well, let's set x equal to 0. What would we get if we set x equal to 0 in our original equation? We would get 0 plus y squared over 2 squared, which is 4, equals z over 5, right? Which, if we work this out, like multiply both sides by 5, you get 5, I'm going to rearrange it. If you multiply by 5, you get z equals 5/4 y squared. And what is this shape? Oops. What is this shape? Hopefully you realize that this shape is just a parabola, right? If you put y here, you put z here, and you get a parabola. Which, look at that. If you look at this on the side, it's a parabola. Now, what about if I set y equal to 0? I would get x squared plus 0 equals z over 5, right? Which multiply both by 5 and you get z equals 5x squared. And that x z, this is also a parabola. Right? So if you're looking at this picture here, if you look at it from this direction, you see a parabola, right? Which is pretty much what we see. Now, if you were on the side and you were looking at it from this side, what would you see? Also a parabola, right? And then if you were looking down on it, what would you see? You would see these circles or ellipses. Okay. So if you look at this, then the traces from one side are parabolas. The trace on the third variable was these ellipses. And when we plot the shape, it looks like this. And we called that a elliptic paraboloid. So it's a paraboloid because this is a parabola, and it's elliptic paraboloid because if you look down on it, these are ellipses. Does that make sense? And hopefully you saw how these traces were able to help us plot this curve. We actually only needed these, and we plotted them, and we already figured it out. But, of course, again, you can go to GeoGebra, and GeoGebra is able to plot this pretty well. You know, other than the fact that typing stuff in's a pain on this. Go back. How do I go? Give me the keyboard. I just want the keyboard. Give me the keyboard. Clear all. Sure. Don't save. Okay, that worked. Hey. Okay, let's try to do this. So we want x squared plus y squared over 4 equals z first degree over 5. Right? And there you go. There's your elliptic paraboloid. Now, if you look at it on one side, you get a fatter parabola. I kind of cheated. I didn't really plot these parabolas, but like z equals 5x squared is actually very tall and skinny. And z equals 5/4 y squared is actually less tall and skinny. So on this side, the fatter side, that's this one, z equals 5/4 y squared. And if you turn it sideways, you get a skinny parabola. That's this one, z equals 5x squared. And if you go to the top, it's ellipses. And that was that ellipse that we saw. Well, I mean, I guess I don't know what one we saw, but as z equals 5, it was plus or minus 2, right? And actually, if we look at this, depending on how we're zoomed in, if I zoom out a little bit, right? Or zoom in, how do I do this? Oh, well, yeah. So like 5, okay, so right now it's about 5 tall, right? And if I look at it this way, it's about plus or minus 2 on the green axis and plus or minus 1 on the y-axis. Exactly what we have there shown. And if you make it shorter by zooming in here to like z equals 2, or sorry, yeah, z equals 2, and now you look at it, well, okay, fine, there's no numbers, so apologize. But you see that it's smaller now, right? Like plus or minus 1.5 on the axis instead of plus or minus 2. So probably I drew this one that I said was at z equals 2, but probably the z equals 2 one was more like that. Pretty close to the same size. Doesn't matter though. Okay, so that's an elliptic paraboloid. And we plotted it using traces. Okay, what's next? So there are two things that we call hyperboloids. So there's what we call a hyperboloid of one sheet and a hyperboloid of two sheets. So hyperboloids. Hyperboloid of one or two sheets. Okay. And we'll see what makes them different when we try to plot it here. Okay. So hyperboloid of one sheet has a formula like this. Nope. X squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Okay, now the key here is actually not which variable is which, but it's the fact that two of them are positive, one of them is negative. Of course, it's assuming you have a 1 over here. So 2 positive, 1 negative. Okay, so 2 variables positive and 1 negative. The one that's negative would be sort of the shape, the surface would be oriented along the variable that is kind of the odd variable out. So in this case, it's z. Sorry. Okay, I think I'm good. Okay, oriented along the variable that is negative. Right? So for example, what I'm saying here is this. So like if I switch the variable names around, if I go like z squared over a squared plus x squared over b squared minus y squared over c squared equals 1, this is still a hyperboloid of one sheet. because it's still plus, plus, and then minus. It's just which variable is where changes, right? And the only difference is the fact that this one is oriented along the y-axis, which means it's just going to be sideways compared to the other one. So this is oriented along the y-axis. All right, let's try to plot one. Let's try to plot one. So I guess before we do it, actually, I guess I can just show you what it's going to look like before we do it. So they look like this. Kind of this shape. And they call it a hyperboloid of one sheet because it's in one piece here, right? It's kind of just like a cylinder that's been squished in the middle. And that's a hyperboloid of one sheet. The ones that's two sheets are actually in two pieces, which we'll talk about when we get there. Let us try to plot one. Let me actually open your homework because I have not, but probably want to make sure we can do the homework, right? 2.6 quadric surfaces. Preview. Sheet, submit. Sorry, I've just got to, just trying to get to a question for us here, which I've got to get past the cylinders before I can get to the quadric surfaces. Maybe I should just talk while we're doing that. Okay. All right. So let's just go ahead and plot one of these, okay? Yeah, here's one. Here's one. So this is in the homework. This is actually directly on the homework. So they give you this equation: y squared over 16 plus x squared over 64 minus z squared over 49. Oh, actually, I lied. They have equals 0 here, so we can't plot it. But I'm going to put a 1 here. Now we can. Okay, so I changed the problem. And they say, what kind of shape is it? Okay. And you should be able to look at this now, and you should be able to recognize that, second degree, second degree, second degree, first, like positive, positive, negative. That means that it's a hyperboloid of one sheet. And the variable that's different, the one that's negative, is z. So that's oriented along the z-axis. Okay. So you should be able to use that information and say hyperboloid of one sheet oriented along the z-axis. Now, having said that, we're going to plot it. Okay, so if we're going to go ahead and we're going to plot this, then what we would want to do is come up with some traces, right? Let's plot it. Okay, so we need traces. Now, if you know that it's oriented along the z-axis, which we do know, then you could just use traces on the z-axis and actually get a good plot. So that's what I'm going to do. I'm going to go let's do like z equals 0 first. So if we do z equals 0, we're going to get y squared over 16 plus x squared over 64 equals 1, right? What kind of shape is that? Right? Think about it. We should know that that's an ellipse. And specifically, what's it look like? If you put x, you put y. On the x-axis, it's going to be plus or minus 8, right? Because it's the square root of the number here. That's like the radius. And then on the y-axis, it's going to be plus or minus 4. And so we get that. Okay, so already if we're going to try to make a 3D graph at some point, I know what I got is on the y-axis, it's going to be plus or minus 4. And on the x-axis, it's plus or minus 8, so bigger. So it's like this. I don't know why. Okay, whatever, it's fine. I don't think that's a very good plot. I think it should look more like this, right? I don't know what I'm doing. That's not better. Okay. So we have that much so far. That's not very good. But what if we go up to z equals something else? Now, what's a good z value? 7's a good z value, right? 7's a good z value. So I put 7 in for z, and so I put 7 in for z, and I'm going to get y squared over 16 plus x squared over 64 minus 49 over 49 equals 1. Or rearranging that, x squared over 64 plus y squared over 16. When you move this 1 over to the other side, you actually get equals 2. And what that does is it's actually going to make these twice as big, right? Because if you divide everything by 2 now, you actually get x squared over 128 plus y squared over 32 equals 1. So what that's telling you is if you go up here to 7, you get the same kind of ellipse as what we had here, but it's going to be bigger now. It's going to be bigger by a value of like square root of 2. So that's not, that's exaggerated, but that's what you get, like an ellipse up there. Something you also want to notice about this is that putting in a 7 here is the same thing as putting in a negative 7 here. So if you put in z equals negative 7 and you work this out, you're going to get the same thing. You're going to get y squared over 16 plus x squared over 64 minus 1 equals 1. So rearranging it, y squared over 16 plus x squared over 64 equals 2 again. Same exact shape, but that's down at z equals negative 7. So that's down here. And we know that the way these shapes work is you just kind of connect the outsides here. And that's how you're going to get that shape. Okay. And so that's a hyperboloid of one sheet. We can do more traces, which I will, but that's the idea for that. Again, we can plot that pretty easily by just typing it in over here. We have x squared over 16 plus, 64 plus y squared over 16 plus minus z squared over 49 equals 1. Enter. There you go. So there's your hyperboloid. Right? Now the reason it's called a hyperboloid is because if you look down from this, if you look down on it, you get those ellipses, right? The ellipses were the traces that we were just drawing. If you look at it sideways, you get hyperbolas. Those are hyperbolas, and if I look on the other direction, those are hyperbolas. We did not come up with those traces, but we could have, and I will momentarily. Okay, so that's why it's called a hyperboloid, because from the side, it looks like a hyperbola. I guess technically, like, they don't, but you could call this like an elliptic hyperboloid, because it's hyperbolas on this side It's ellipses on this side. So if you called it elliptic hyperboloid, that would be basically what we did when we called the other one elliptic paraboloid, right? Now, the reason, if you look at the list, elliptic hyperboloid is not actually one of your choices. So you wouldn't call it that. But if you did, you wouldn't be really wrong, right? It's the same kind of language that we used to name the other one. Okay. Now, if you look at the traces from the side, traces from the side, it's a, right? Like if you set one of the other variables equal to 0, not z. So if you set like x equals 0, what do we get? So if you set x equals to 0, you end up with y squared over 16 plus 0 minus z squared over 49 equals 1. Sorry, let's try to remember it as we go. So of course that's y squared minus 16 minus z squared over 49 equals 1. And what would that trace look like? So we're in the x and the z plane. Sorry, the y and the z plane, y and z. So if you go to plot this, then what does this look like? So the way I think about it is this. If z is 0, so think about crossing this off, because this is supposed to be a z. If z is 0, no, don't erase it, dummy. If z is 0, this is gone. So if z was 0, we would have y squared over 16 equals 1. Which would be like, so if you had y squared over 16 equals 1, then that would tell you that y has to be plus or minus 4, right? So that tells me that this goes 4 over here, negative 4 over here. These dots are on there because what I did was I set z equals 0, which is the z-axis here, to get those points. Now, if you try to do it the other way, if you tried to set y equal to 0, you would get 0 minus z squared over 49 equals 1. But this equation here has no solutions, right? So that tells you that actually along the z-axis, it doesn't intersect. So if you set one of them equal to 0, the z-axis, then you get something you can solve. If you set the other variable equal to 0, like this, you get something that you can't solve. So that's the axis it doesn't go through. So once you know that, you kind of know that the hyperboloid goes like that. I'm not really going to cover how to plot a hyperbola in this class. That's like an algebra thing. But that's what it looks like from the side. And again, if you don't know how to plot that, you can come here to Wolfram Alpha, and we could plot whatever it was. What was it? Like y squared over 16 minus z squared over 49 equals 1. And you just get the plot that I plotted. Okay, so it's a hyperbola. So I did that wrong, so I have to do that. Come back in. Okay. So that was a trace from the other side. It deleted my hyperbolas. And if you set the other variable equal to 0, if you set y equal to 0 in the original equation, you get x squared over 64 minus z squared over 49 equals 1. And that's still going to be the same kind of deal, where you put the z-axis there, x-axis there. And if you work that out, you're going to get also hyperbola there. So set one, like the traces along one, like the y equals 0 traces on hyperbolas or hyperbola. The x equals 0 trace is a hyperbola, and the z traces are ellipses. So from the side, it's hyperbola. From the top, it's ellipses. Okay, that's a hyperboloid of one sheet. Okay, next thing. Okay, so the next thing they do actually is they don't plot all of these. They just list all of the things that you need to know. So what I'm doing is I'm going to your textbook and I'm going to steal their picture because I don't want to draw all these right now. And you don't want me to draw them because you already saw how I draw. So table of contents, quadric surfaces. Hey, look, it's our friend the cylinders. There's our friend elliptic paraboloid. There's our hyperboloid of one sheet. Here's all of our shapes. So, oops, come on, stop. Oh, I hate computers today, man. It won't let me make that smaller. It did let me make it smaller, and then it stopped letting me make it smaller. Close that. That was worse. That's really frustrating. Just add to the photos, but I know it's not going to let me add it to this right here. Right. The liar. Oh, no, it didn't. Okay, I lied. Okay. Sorry about that. I just want to put these here. So here's some of the quadric surfaces that we should recognize. So what can we say about them? So we already talked about the details here, right? So for an ellipsoid, stop. For an ellipsoid, it's positive, 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 all second degree, right? And in the traces, no matter what variable you use, ellipses, 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 ellipsoid. Hyperboloid of one sheet. That's what we just plotted, right? So positive, positive, negative, second degree, second degree, second degree. Okay. And then the traces on one, it was an ellipse, then hyperbola, hyperbola. And we get this shape. From the side, it's a hyperbola. From the top, it's an ellipse. Now, hyperboloid of two sheets, we didn't talk about, but notice how you can tell the difference. Look, plus, minus, minus. This one was plus, plus, minus, right? This had two pluses and a minus. This one has two minuses and a plus. That's how you'll tell the difference. And why did my brightness just lower? Oh well. And when it's two minuses and a plus, it turns out that you get something that's split up into two pieces. And it's split up into two pieces because if you think about what happens at z equals 0, if you set z equal to 0 here, so like you just delete this variable, it's negative x something x squared, negative something y squared equals 1, which has no solution because a negative number plus a negative number does not equal positive 1. So at z equals 0, there's no surface. Okay. I'm sure we're going to plot one of these in a minute, so I'm not going to go into too much detail now, but that's why it's split into two pieces, because there's a region where there is no solution to this. Okay. After that, then notice that it says like z equals p. It says an ellipse or the empty set, no trace, empty. But then from the side, hyperbola, hyperbola. Okay. So those are some of the shapes. They're not all of the shapes because There's 3 more down here that they have. Add to photos. Trying to make this big. Okay. Too big. Okay. Come, what? Stop. Why did you do that? Move down. Okay. So then we got these shapes here. Why does it keep covering up the other one? That's so stupid. No. Oh, because it won't go off to the second page. That's why. All right, sorry about that. So then we got some other shapes here. So one shape is the cone. And if you look at this equation, plus, plus, minus, plus, plus, minus was just like the hyperboloid of one sheet, right? So what's the difference? The difference is where well, the other side of the equation. Here there's a 0. And on this one, there's a 1. And basically this 1 is like if you set z equal to 0, so imagine this disappearing, you have like x squared plus y squared equals 1. That's a circle with the radius 1. Whereas here, if you set z equal to 0, you have x squared plus y squared equals 0, which is like a circle with radius 0, which is a single point. So that is what's going on. And technically, if you did like this same thing, like x squared plus y squared minus z squared equals -1, that would be saying like at z equals 0, the radius is -1, which is nothing. And that's actually where you get this from, right? Like if you multiplied this by everything by a minus sign, it would be minus plus plus, but then a -1 here. So like in the center, the radius is -1, which is why it's gone. Okay, enough of that. Elliptic paraboloid, we already saw. X squared, y squared, but then this is only first power. And we got this. And hyperbolic paraboloid. So again, notice this is first power, right? So this is first power plus plus. This is first power plus minus. So the plus and the minus give you hyperbolas when you look at it from the top. Whereas this gives you an ellipse when you look from the top. Okay, anyway. So what shape is what? All boils down to what are the signs on the x, the y, and the z, and what are the powers on the x, the y, and the z. And also, on the right-hand side, is it a constant or is it 0? Okay, so that's quite a bit of work to deal with all of these. Let's plot something or do something. Let's do one that's probably a little bit annoying, just so we can do one. Okay, I gotta close that again. Open it up. Okay. Okay. Just so it doesn't look like it ends. What we're doing, we're going to do an example. Okay, so what's an example? So here's an example. Identify the surface. (9x² minus 18x plus 4y squared plus 16y minus 36z plus 25 equals 0. All right. So obviously you're going to look at this and notice that it looks different than what we've done before, right? Um, so it's a difference because there's all these first degree terms, and also the coefficients are not um, in the denominator, and so on, right? So first thing to do is going to be to realize that if you've got these first degree terms in there, you're going to have to do what we call completing the square, which should not be new for you, but still. So if you have second and first degree terms for a variable, you're going to have to complete the square. So for the y and for the x, we have to complete the square. Not for the z, because there is no second degree z. So there's no completing the square to do. But for these two, you do. So how do you complete the square? So you got to remember how to do this. What do we have for x? 9x squared minus 18x, right? So that's what we have. To complete the square, what you do is, first of all, if you have a coefficient like this, factor it out. Like so. Okay? We don't want a leading coefficient. Then what you want to do is, for that middle term there, you want to divide the middle coefficient. I should say first degree, not middle. So divide the first degree coefficient by 2 and square it. So in this case, negative 2 over 2 squared. So if I do negative 2 over 2, I get negative 1. Negative 1 squared is 1. Okay? So then what you do is you are going to add and subtract the result of the previous thing. Add and subtract result of 2. So I have 9 x squared minus 2x. And then what I'm going to do is I do plus 1 and minus 1. And it's 1. That's why that's 1. So this one is this one. Okay? And then what you do is the first three terms in here are supposed to factor as a perfect square, trinomial. So that's factoring. And what will we get? We're going to get, so factor, we get 9 parentheses. The part that I underlined is going to be x minus 1 quantity squared. And then I still have this minus 1 left over from the plus 1 minus 1. I had to plus 1 minus 1. That way I wasn't really doing anything. Okay, so that's how you complete the square. So I did that. We also have to do it to the other one, which was 4y squared plus 16y. So 4y squared plus 16y, was that it? Yeah. So same deal. Factor out the 4. Take that middle term, divide it by 2, and square it. 4 over 2 is 2. 2 squared is 4. So you have 4y squared plus 4y plus 4 minus 4. That part should factor as a perfect square trinomial. So you end up with y plus 2, looks like, squared, and then minus 4. And we get this. Okay, so I just completed the square twice. So now if I go back to the beginning of my problem here, I've got, where is it? There it is. duplicate that, drag it down. Okay. So we just completed the, you kidding me? I don't know what it is about today, but it is not going good. Nothing's going good. Okay. So now back to where we started. So we just replaced this and we replaced this with the first one turned out to be 9 x minus 1 squared minus 1. The other one turned out to be 4 y plus 2 squared minus 4. And then we have minus 36z plus 25 equals 0. Okay, so then what you're going to do is just kind of multiply out the multiply this out, the 9, multiply out the 4 here. So we're going to get 9 x minus 1 squared minus 9 plus 4 y plus 2 squared minus 16 minus 36z plus 25 equals 0. So then what you want to do is kind of just combine all your constants here. Just collect like terms. The constants together. So we get 9 x minus 1 squared. I'm not going to write the minus 9. 4 y plus 2 squared minus 36z. And then what do I get for the constants? So I just underlined them all. We have a negative 9, a negative 16. That's negative 25. Negative 25 plus 25, they actually all add up to 0. They all add up to 0. Equals 0. So we have this. So then I'm looking at this form here, and what I've got is I've got an x squared, a y squared, a z to a single power. If I look at my forms, I notice that whenever there's a single power, single degree, they always put that on the other side of the equation, right? Like z by itself here, z by itself here. The first degree goes by itself on one side, if you have one. So let's just move the z over, because we're just going to try to make it look like the samples. Move z over to the other side. So 9 x minus 1 squared plus 4 y plus 2 squared equals 36z. That's almost what it looks like, but we also know that they don't leave a number here. So we should divide off that 36. So we should divide that off. And if we do that, we get like 9 over 36, x minus 1 squared, 4 over 36, y plus 2 squared equals z. And we can simplify those fractions. 9 over 36 is what? Wait, does 9 go into 36? Right? Yeah, it does, right? 4? Okay, sorry. 9 and 9 is 18. 18 and 18 is 36. All right, so that's 4. X minus 1 squared over 4. 4 over 36 is 9 on the bottom. So y plus 2 squared over 9 equals z. Okay, so we do this. And what you need to realize about that is that this is basically, this is z equals just x squared over 4 plus y squared over 9. But the minus 1 here and the plus 2 here are vertical, not vertical, they're shifts in the x direction. Shifts to the 1 plus 1 in the x direction and minus 2 in the y direction. Just like when you learn transformations in when you graph functions in 2D. So this is just this, but shifted plus 1 in the x direction and minus 2 in the y direction. Either way, the actual shape here, right? Z and then plus and then plus. Z and then plus and then plus. So this is an elliptic paraboloid, and the center has been moved a little bit. So this is so overall, we see that our surface is an elliptic paraboloid. Wait, is it? I guess so. Yeah. An elliptic paraboloid centered at, like, instead of 0, 0, 0, it's -1 in the x direction, or sorry, +1 in the x direction, -2 in the y direction, and nothing in the z, right? There's no, like, if we had like a +9 there, that would be shifted 9 in the z direction, or -9 actually, but yeah. Okay, so it's an elliptic paraboloid. So if you go to plot this, then like what it would look like, which we weren't asked to plot it, but if we were asked to plot it, then x, y, z, normally an elliptic paraboloid is like that, right? But ours, the bottom has been moved +1 in the x direction, -2 in the y direction. So instead of here, it's, right, +1 in the x direction, -2 in the y direction to get here. And then you have your elliptic paraboloid. Now you could have just gotten that from doing the traces, right? I was just showing you how you do the math to identify it, where you're starting with this jumbled mess here, and what you got to know is complete the square, and then just try to make it look like one of these that you're supposed to have seen. Okay, that's kind of it. Let's see, there's one other question here, I guess. Okay, yeah, I think that's it. So let me try to find one more or something to do. Yeah, here's one more, I guess. Here's a homework question. Determine the center of the hyperboloid of two sheets. All right, that's the one that looks like this. We haven't actually graphed one of those yet, but determine the center of the hyperboloid of two sheets with equation 6x squared minus 2y squared minus 12z squared plus 12x minus 4y plus 24z minus 20 equals 0, right? So it looks like a mess. And you just do exactly what we just did in the previous problem. So collect your variables, right? So your x's go together, 6x squared plus 12x. Then you got your y's. We got minus 2y squared minus 4y. Then you got your z's. these. So minus 12z squared plus 24z. And then what's left? I guess just that minus 20, like that. And so each of the things that I wrote in colors here, each variable needs completing the square. So you go like 6x squared plus 2x, leave some space. And then for the y here, you go pick a darker green. No, I won't. Minus 2, factor out a minus 2, and you'll have y squared plus 2y, leave some space. For z, you've got factor out a minus 12, and you'll have z squared minus 2z, leave some space, and then you got minus 20 equals 0, right? So I just factored out the constant because that gets in the way when you're completing the square. For the thing you have to add, remember how to do that. You take this middle term, divide it by 2, and square it. So we're taking the 2 divided by 2, you get 1. 1 squared is 1. So plus 1 minus 1. On this one, again, 2. So divide by 2 to get 1. Square it to get 1. So this one's also plus 1 minus 1. Here you've got a minus 2. Think, right? Because these are different signs. Divide by 2, you get minus 1. Square it, you get 1. So this is also plus 1 minus 1. There's no reason why those all are the same. They're just making it that way. And then we factor. So the point is, you got to know how to factor this, this, and this. We're going to get 6 parentheses. The part that I underlined factors into x plus 1 squared. And then there's that extra minus 1. Then here we've got minus 2. The part that I underlined factors into y plus 1 squared. And then there's an extra minus 1. And then on the last one, minus 12. Z, this one's got a negative here, so it's going to be z minus 1 squared, then minus 1. And then you got your minus 20 equals 0. Actually, this is already enough. Like, this is already enough to see that the center is going to be minus 1, plus 1. But, if you want to keep going to simplify this, then you would, multiply it all out. So like 6, x plus 1 squared minus 6, minus 2, y plus 1 squared, minus 2 times minus 1 is plus 2. And then minus 12, z minus 1 squared, plus 12 minus 20 equals 0. So then you can do all your variables first, and then collect all your constants. So we got this negative 6 plus 2 is negative 4. Negative 4 plus 12 is 8. 8 minus 20 is negative 12. So we get that. You would move this 12 over to the other side. So you move the 12 over to the other side. So you get that. Then you divide everything by 12. So you divide everything by 12, you get, it's going to be x plus 1 squared over 2 minus y plus 1 squared over 6 minus z minus 1 squared over 1 equals 1. So what you can do here when you're looking at this, right? First of all, plus, minus, minus, so 2 minuses. That tells you hyperboloid of 2 sheets, right? So hyperboloid of 2 sheets because it's plus minus minus, and there's and everything squared, all second degree. Also, the variable that's different than the other two, right? The two that are the same are the y and the z, negative, negative. Z is negative, y is negative. So these have the same sign. The one that has a different sign is x. That tells you that it's oriented along the x-axis, right? It's always oriented along the variable that's different than the other two. So it's oriented along the x-axis. And for the center, you do the center like you do the center of an ellipse or anything, right? So it's going to be the numbers that are here, but with the sign changed. So it's been moved -1 in the x direction, -1 in the y direction, and +1 in the z direction, right? Plus, plus, minus, 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 plus. Okay, so actually you can draw this pretty well. So like I know already that this is a hyperboloid in 2 sheets. So it's 2 pieces. I know the center is at -1 in the x direction, which is back here, -1. -1 in the y direction, which is to the left. So we're back here so far. And then +1 in the z-axis. So that's actually up. So that's that way, and then up 1. And that's the center. However, it's a hyperboloid of 2 sheets and oriented along the x-axis. This is the x-axis, right? So basically, at this point here, that's up in space, you can draw a straight line in the z-axis or along the x-axis, parallel to the x-axis, and that's where it's oriented along. So it's like an ellipse. Can't really draw this because it's coming at us. That's pretty terrible, but stop erasing it. Dang. This is like the side. We're looking at it, and then okay, that looks pretty bad. But if you go to plot this, you'll see what I mean, which I will plot it, and then probably will be done at that point. So if I go here, I'm going to erase this, just delete. And I go, come on, let me scroll. Just let me scroll so I can type. So stupid. Okay. What do we got? Parentheses. X plus 1 parentheses squared over 2 minus parentheses y plus 1 parentheses squared over 6 minus parentheses z minus 1 parentheses squared equals 1. Go. Okay. This is kind of not the best drawing here. I want to rotate you. Okay, there we go. So this is what I was kind of trying to draw. Can't really zoom in very well. So like there's like, if you look down from the top, if you were looking down from the top like this way, right, then what you would see is on the x, if you had x and then y, then on the x-axis it would look like this. That's a really terrible color, I'm realizing. It changed the color, right. So this is what you're going to see when we look down from the top, like this. So the x-axis is that red axis. And then if you look at it from this side, like what I was trying to draw here was what this oval that you're seeing in front of us. And if you look at the top, you can see that. Anyway, so I couldn't really draw that very well, but hyperboloid of two sheets. And so we could get all that from the equation, what variable is positive, what variable is negative, which ones are second power, and so on. Okay, you don't really actually have to do, I don't know if you have to do much graphing at all. You have to like identify it from the equation. Oh, you do have to graph, or you have to graph traces. Okay, that's actually obvious what to do. Okay, so I think we're done. We're an hour and 40 minutes in. That seems like plenty. You can graph these by using traces. You can identify them from their equations, and that's really what they expect you to do. All right, so have a good day. See you next time.